Okay, so this is the graduate course. It's a physics course. It's listed as a physics course. That's why it's called Scientific Computing for Physicists. But it really applies to all physical sciences. The idea is that if you've got the computational components to your research, and many of us do these days, then you don't want to reinvent the wheels and find out all the things by yourself. But there's not many courses that'll show you sort of the best way to go about attacking your computations. You will have had the theory, you might even had some numerical methods courses, but not quite sort of the nuts and bolts of how do you set up this properly and not spend months figuring out that you did things the wrong way. So it's going to take the whole winter term, 12 weeks, but there'll be a week, a reading week that we skip, so we'll end somewhere in April. And there's some prerequisites, some skills that we assume you either bring to the table or are able to pick up. You have to have some programming experience. We're not teaching you how to program here. So preferably in a compiled language, although if you've done extensive scripting in Python, and by which I mean you run a script and you don't touch it until it's finished, you might be able to pick up as well, but it'll be a little bit more of a steeper learning curve than if you've already done C, C++, Fortran, even Java or C#, something like that. It will be a plus. Now, we have to choose one language to work with as our compiled language in the course, and we chose C++, mostly because while it might be initially a little bit easier to do Fortran, in the world outside of academia, you'll encounter C++ or C-like languages more, so you might as well get used to those. We're not using very fancy stuff of C++. We're just using it as a base language. We're not going to do heavy object-oriented programming or templates or anything scary, but that will be the language we're using. So one of the things that we will do in the next few lectures, actually, is to review C++, to sort of give you an idea of what it is that we will be using in the course. We'll be going too fast for you to pick it up, but if you've seen these in another language, you'll see, oh, that's how I do it in C++. And if you haven't, at least you know what you should read up on yourself. What the real topics are not C++, are scientific computing, programming skills, optimization, and a bit of parallel programming towards the end. So we've roughly divided the class in 3 parts, or the course in 3 parts, that you can actually also take as many courses if you so desire, although I would strongly suggest taking the whole course as a whole. So we'll start the first 4 weeks with scientific software development. There's a few things in doing software development for science that are more important than just generically knowing how to program, and we'll cover them here. So we'll go into the C++ stuff. We'll go into version control, automated builds. We'll look at modular programming and debugging. Then the second part, so those are very important skills for you to become productive and not waste more time than you need to on your project. So it might seem a little bit more not so scientific, but it is, because it's all the support stuff that you will need. Then the second part, we're actually going to do some numerical tools that are very common in physical sciences. So we'll talk about floating point arithmetic. We'll talk about random numbers. We'll talk about ordinary differential equations, partial differential equations, Fourier transforms, sort of building blocks of scientific computing. And we'll have a focus on using existing libraries that are really good at doing this so that you don't really have to code these in. A lot of the best practices in this field come from not trying to do more than is necessary, not reinvent the wheel when it's already done and when it's probably done better before you. Just reuse what you can. And then the last part, we're going to look at performance. And if your computations become large enough that you need many, many weeks for them to compute, it actually matters how fast they are. And so we'll look at profiling, optimization, parallelizing, that is to say, use more than one of the cores in your machine, or maybe even multiple machines at the same time. So we'll do that towards the end. This is a bona fide physics course, so if you're allowed to take a physics course in your graduate studies, you can take this for credit. Physics, astronomy, and also chemistry allow a different way of taking these courses, as well as modular courses where they can bundle, I think, 3 of them together. You can use the parts of this course as such if you want, but just let us know, okay? As I said, I would really suggest just taking the whole course. It's worthwhile. Okay, so you are here at SciNet. Believe it or not, you are still at U of T. There's actually quite a few U of T labs now in this building. But what is SciNet? You might have not heard of SciNet. So SciNet is essentially the supercomputer center of U of T and the associated hospitals. So we are here. The large supercomputers are actually further north of the city. But we're here because we want to be close to the researchers to help you. And so we provide these high-performance computing systems. We support the users, the software on it. We also give a whole bunch of courses, anything from the command line to parallel programming and visualization and machine learning. And this is one of these cases. And more of these teaching efforts of ours are going to become university courses. So this is one of those that grew out of just local trainings, not for credit, and are now fully credited. SciNet itself, this is important for you to know later on, is then a partner of Compute Canada, which is sort of the national organization that, let's say, coordinates the supercomputer centers all over, or the access to supercomputer centers all over Canada. Now, there's going to be a fair bit of homework in here. In fact, we're going to have something of the order of 10 assignments. They're all going to be programming assignments. And initially, the first few you can do on your own computer as long as you have the GNU compilers like G++, a utility like Make. So if you're working on a Windows machine, probably the least resistance of getting a Unix-like environment is to install Cygwin. I should warn you, it takes a little while to install, but that seems to be the one that has the least issues. If you're on the Mac, there's various flavors of the GNU compilers that you can use. Go to this website, hpc.sourceforge.net, and download one of those. They tend to give the least problems. If you're on Linux, fine. You should be good to go, or at least you can install all of these quite easily. And make sure you install something called Git as well in that Linux environment. So if you're working in Cygwin, you need Git in Cygwin, not in Windows. However, towards the end part of the course, and actually it's useful to get it as soon as possible anyway, you'll be working on the supercomputers of SciNet. And so for that, you need an account. This is our most commonly used supercomputer. It's called a GPC. It stands for the Prosaic General Purpose Cluster. And you'll need an account for it. And so part of your first homework will be to get this account. It's not hard, but there's a couple of steps to do. By the way, SciNet accounts are available for all academic researchers in Canada, as well as their students and postdocs and even international collaborators. But it has to initiate from the researchers or from your supervisor. And so if you already have an account, who here already has a SciNet account? A couple. So you guys are fine. Otherwise, roughly the procedure is as follows. You have to have a supervisor that has a Compute Canada account. It doesn't cost anything. It's free. So that's your first thing. When you go to your supervisor, you need an account. You say, I don't want to spend. No, it's free. Okay, good. So you get a Compute Canada account to get sort of access to the national level. And then you need a local level account, a SciNet account, which is really a click away once you have your Compute Canada account. And then once your supervisor has it, he can sponsor you. So you get your Compute Canada account and then your local account to follow. All of that is also on this particular website. By the way, the slides are on the education website. And so all of these should be properly linked, and you should just click on them and find your way. As I said, you have a few weeks to get this started. No, usually it doesn't take more than a week or so to get the account set up. But if you find any difficulties or you find your supervisor is a little bit unwilling or hesitant, or just let us know and we can help you out. Chances are your supervisor already has one, especially if you're in one of the sort of traditional HPC fields like physics, chemistry, astrophysics. Quite likely already has one.
What departments are you?
6 physics, 2 astro, 3 chemistry. Hey, that's good.
Or is anybody
Okay.
Hey. Very good.
So chances are most of your supervisors already have the account, and it will be too.
The best course is the most important course. And that.
Right. So.
I leave you in the best hands.
Yes. So that's Danny. His name is on the course, but most of the teaching will be done by myself. I'm Ramses van Zon, Marcelo Ponce in the back there, and Scott Northrup, who's not in the room right now. We're analysts here at SciNet, so our job is to support users and to teach users, and so this is part of that. We're going to use the course website quite extensively, especially when we do assignments. So I put a link on here again. Although to find the slides, you have to be on that link, so it's a little circular. The lectures will be on there. Recordings of the lectures will be posted. If you look on the right here, there's a recording section. There's a lecture section, assignments. We'll give assignments on Tuesdays, and then you'll have a week to complete them. There's a late policy that I'll explain in a second. And you can submit that homework on the website as well. So that's useful for you because you can find your submissions back on there. Useful for us because all the submissions are in one spot for us to grade. And the grades will be posted on that same site. Once you have your SciNet account, or if you have a SciNet account, that account is also your account for this website. While you don't have your SciNet account yet, you have a temporary account for this education. So is there anybody here that doesn't have an account on the site here, on the web education site? Okay, so maybe come to me after class and we can make sure that you're all set up. If you're going to take it for credit, signing up on this website is not enough. You'll have to do it through the official channel, so sign up to Acorn, etc. I think you have until about the end of the month to do that. So this is important for the actual crediting. But we'll be using this website, not Blackboard, not Acorn, for all the sort of day-to-day business. Then about the grading, we're going to have about 10 programming assignments. Some weeks we just don't learn enough new stuff to do an assignment about. It'll be, or not a programming assignment anyway. And the average of those will be your grade. So there won't be a final exam or anything like that. So now you have to submit all of these homeworks, but should something happen, we're reasonable, so just talk to us. There is a standard penalty policy for late submissions. We find it helps to have this just in place, so you know where you're at. If you're a day late, there's a half point of 10 points out of the type 10 points off, and then that up to, I think, 7 days late. So you can lose 3.5 points, and if you think you did such a good job that doesn't matter, I guess you could take a week longer. But this way, a week after the actual due date, we know all our submissions are ready, and we can give you your grades, because we can't really start grading until we have all your submissions. So it really is a policy that helps you get your feedback as soon as possible. And finally, this is what our lectures are here. They'll be here for all of the lectures. There's also going to be office hours, which I think we've said on Wednesdays from 2 to 3, which will be here, or at least in the offices. So we'll see whether this room is booked or not. But let's say in principle it's here unless it's booked, and then you'll just ask in the front desk, which is right around the corner, where I am, and you'll find me. Don't be shy. Come to the office hours. They're really the best way to get sort of face-to-face questions answered. But if you have other questions during the course and you can't make it, or they're a little bit more urgent, Courses at SciNet@utoronto.ca is the email to use. All of the instructors are getting that. And so that's the appropriate way to contact us. There'll also be actually a forum on the website, which you can all see. Depending on how active you guys are, that determines whether that forum is really working or not. Some courses, people are active and that forum works. Other courses, people prefer email and you just see 1 or 0 questions. But we'll put it there, and it's for you to use. We'll take a peek at it every now and then as well. Attendance isn't mandatory here, and we're recording the lectures. Of course, it's always easier to just come and listen to the material. And we're working on broadcasting, possibly. So that's about how we've organized the course. What we are actually going to do. Any questions about the organization, by the way? As I said, if you have more questions, just ask them later. So there'll be these 3 parts, and the first part, we're going to do some introduction to C++, for which will take about 2 lectures. And then we'll dive into something called modular programming, which is a helpful technique to make sure that your project is sort of maintainable by yourself as well as by others that might use it later. We'll then look into automated builds with a thing called Make. And after doing a bit of that sort of software engineering, we'll go back to C++ and we'll look how you deal with things like arrays and other data structures, objects, and how you do debugging, which is a useful thing to know. And then towards the end of this section, we'll look into version control with a thing called Git. And we'll do some unit testing material as well. So that's really software development, and they'll make more sense as we see them come along. Using those from the beginning can save you a lot of time. I wish I knew all of these things before I started my scientific programming career. Get a lot more done. And then the second part is about numerical tools. So this is sort of the overview. We'll look at numerics and what kind of errors can happen with floating point, ordinary differential equations, molecular dynamics, partial differential equations, root finding, linear algebra, fast Fourier transforms, and random numbers, Monte Carlo. So we can do this much because we're going to offload all of the implementation to libraries. And that's going to be the theme of that. How do I use libraries? How do I make sure that they are used properly? And how do I not reinvent the wheel? So these aren't going to be theoretical about these topics. We assume that you know a little bit about them, and then we'll show how to do them in your software. And then the last part is about high-performance computing. And the first thing that you'd want to know about performance is how can I improve it? And is it even possible to improve it? So profiling tools are a way to look at your existing code and see where the bottlenecks are. And then we'll look at how one could just improve the existing code, looking at what's called serial performance. That's to say, we're not doing anything in parallel yet. We'll look into parallel computing net. So parallel computing is whenever you use more than one CPU or core or whatever you want to call it at a time for your computation. So ideally, that would speed things up if more workers are working on the same problem. We'll look at 2 ways of parallel programming as well. One where these CPUs can see the same memory, so that's if they are multi-core machines, or distributed parallel programming, which is when you have separate computers that have to talk to each other through a network. They don't share the memory. It's a little bit more complicated, but gives you, in principle, an unlimited size of problems. So that's the outline. I don't know if I've been talking for 20 minutes. Any questions about that? Because now we can actually start looking at some software development. Okay. No, let me do that now. I think everybody's here. As I said, it's not mandatory, but we like to know who was here. So if you don't mind passing this around. If your name's on the list, a check is enough. You don't have to sign it. If it's not on the list, there's some room at the bottom. Put your email then for sure if you're not there. Okay, So who here has never programmed? Excellent. Right. So what I'm going to say right now should be very trivial, but I want to sort of demystify a few things and set this up. So programming is telling the computer what to do, right? So now, ideally, you'd like to tell the computer what to do rather than exactly how to do it. Computers aren't smart enough for that. So rather than saying, OK, I want to know what the spectrum of hydrogen is, and then the computer goes off, we will actually have to put in a model and have it solve some eigenvalue problems and give out the spectrum. All these steps are then going to be subdivided, et cetera, et cetera. So we have to be way more explicit. Now, not every programming language is the same, but a lot of them work in a way where you, and this is the way that a computer works, where you basically have what's called a state. State is everything that's held in memory, more or less. You operate on that state. There's a set of predefined actions: read a variable, add to variables, store a variable, write to disk. A couple of predefined actions that you have at your disposal, sort of the basic building blocks. And with that, you try to build everything. So different languages will have different building blocks, and therefore different pros and cons. But using those building blocks and building something bigger, that's really what you're doing when you're doing programming. So when you're doing say, numerics, typically you want to implement some sort of algorithm. You want to compute something. There's a way to compute it. You've looked it up, or it's there. Now you have to code that in. So you have to find a way to use those building blocks to implement that algorithm. You can do that in a, so suppose you've done that. There's a couple of ways you can subdivide a program, and just mentioning these terms here. There might be different subparts of this algorithm that can be grouped together. And so you could have what's called a function, or a procedure, or a subroutine. They're all more or less equivalent set of actions that implement an algorithm or part of an algorithm. So you can think of this as building a new, bigger building block out of little building blocks. They're just building blocks still. They don't run themselves. The program is something that you can run. Right? So there's a bit of a difference between the two. Once you have a function, you could use it, but it's not doing anything. It's just sitting there. It's like an appliance. If you don't switch it on, you haven't done anything. Right? The program is the thing that switches it on and makes it all go. The program is the thing that can get input or output. The function can just get some parameters. We'll see that. So when we do programming, we basically usually write building blocks and then write a program. Coming back to this idea of state, the state of a program, and you can, I find it easiest to think of a simulation here. Suppose you're simulating, I don't know, formation of a galaxy. You start with gas, some particles there, and then you see in time how they progress. Having all the positions of these particles at any given time would be the state, and as you compute the next time step, that state changes. You can keep your own application in mind. But so the state changes as the program progresses. Usually you store this state in what are called variables. So there's data, there's numbers, they have a name. Basically, that's a variable. And so data almost always has a name. Okay? So you have your variable and you have a name. And then the program acts on those variables. The data is stored somewhere, right? So all of this is supposed to live in memory. And so that's sort of the structure of state. You have memory that has a name, and now it's called a variable. Variables change as the program goes along. That's why they're variable. We might need to take some decisions. So whenever I talk about control structures, what I mean is basically an if statement. If the density is bigger than that, do this. If it's lower than that, do something else. And then often you have to have repeated actions, and those are called loops. I took these concepts, because they're not specific to C++ at all, from an old paper, it's older than I am, 1971, of The Art of Programming by Dijkstra. This was true then, and it's true now. These are the basic building blocks. Even if you do more abstraction, this is still what's being done by your program. Computers kind of work this way, and so your program kind of works this way. There are higher level languages where it looks more like you're saying, I want this done, now computer, go figure it out. But under the hood, it's still doing this. And so if you want to be able to do high performance computing, you will need to know what the computer is doing. You have to think in this way. You sometimes have to go away from the higher level, as nice as it might be, because your stuff just doesn't get done otherwise. So C++ is one language that is high performance because it's really close to how the computer actually works. You can do low-level programming, so you can really tune your implementation to the hardware or to the way that the computer works. And by knowing a few things about how the computer works, you can get your program to be 10, 100 times faster. So this can really matter. C++ is ubiquitous, and you can find it on almost any platform. It's highly standardized, which means that a well-written program, and by well-written I mean conformant to the standard, will run on any of these systems. It has a whole bunch of useful libraries. That means there's extra building blocks that you don't have to implement. And it's naturally a modular programming language. So you can build your own building blocks. And once they're done, they can't interfere with other building blocks. That's a good thing about modular design. There are some disadvantages as well. Because it's kind of low level, it has the capability of abstraction, but it doesn't come with a lot of it. It's more labor intensive. In other words, you have to write more lines of code to get the same thing done than, say, in Python. And the more code you have to write, the more errors you can make. So it's more error prone just because of that. And the syntax is a little bit cryptic at times, and so that, again, makes errors a little bit more common. If you want to do high-level programming, this is totally possible. You can write this, but it's up to you. Right? It's not interactive, and that is a downside. If you're just sort of exploring something or exploring an algorithm, C++ is a tough way to go about. Environments like Python or R, where you have a command prompt, you type something in, you try something, it doesn't work, you try something else, so the variables are still there. You don't get that in C++. So you write your code, you compile it, you run it, and then it works or it doesn't work, and then you go back. Again, that makes it more labor intensive. Things like graphics can be hard, so we will stay away from graphics for most of the part. And there's still performance pitfalls that you can do, especially if you're trying to do the high-level programming in C++ anyway. So finally, who here is also familiar with Python or R? Right. So Python is almost the opposite. It's not fairly labor-intensive. It's harder to make errors just because you write less, and the syntax is a bit more understandable. But it's not high performance. You can't get down to the sort of machine level. It's becoming more ubiquitous than it didn't used to be. And so we're staying with C++ because this is going to be the way you get high performance. So you're here to take the next step from, okay, it kind of works, but it takes 3 years to do this computation, and I don't have that time, to, no, I want to do a computation for real. There's no free lunch, so even in Python, I can write horrible code, and in C++, you can write inefficient code. You have to kind of know what you're doing, so we'll see. But that's why C++, mostly because of the performance and the fact that it's highly standardized. So let's look at some C++. By the way, these slides are for both lectures. We're not going to go all the way to the end. But it's easier to do the whole C++ introductions one. Then that way you have one PDF that you can look through later to go, okay, how did this go. So C++ is really sort of a derivative of C, or at least it started that way. And they're both compiled language. That is to say, you write your code, a compiler turns it into machine code, and the machine code can be executed. This machine code is native to the processor. So once you've compiled it, that particular program will run on that system, but not necessarily on other systems. And C itself, which is sort of well, in retrospect, you can say it's a stripped-down version of C++, but it's meant for system programming. That's why it has a fairly small base that is sort of mapped on early processor technology, what the processors could do. That's what C did, but so that's good, as we say, because it means that we can sort of tune for processor-specific stuff. But it also means that a lot of the functionality isn't in the language, but is in libraries. And the same is true for C++. Although the language has grown tremendously from C, and it's almost a superset of C, we will rely on libraries to do a lot of the legwork. Just to be clear and to have some sort of standard, we're going to follow the C++ 11 standard here. And so if you install your own compiler, make sure you have version 4.8 or something that can do C++ 11 properly. ECC is up to version 6 now, so that's, unless you have a very old machine, it's probably okay. What does it look like? So here's a basic C++ program. And it has a bunch of the typical elements in it. It'll print hello world. So I give away what it does. So suppose this is in a file hw.cc, and I'm on a command line. And so you're going to have to use the command line at some point. So if I have G++ installed, I should be able, and hw.cc is the file that's in this directory, this command will compile it for me. So G++, and I set the standards explicitly to C++ 11. That's that -std equals. That's all that it does. And the -o sets the output name. So this will create a new file called hw with no extension, which will be the executable. And then some extra flags that we'll talk about later. So this takes the code, compiles it, and then since I'm not getting any message, it means it was successful. And then I can run the code by typing the name of that executable. We also have to say where it lives, and it lives in the current directory, and in Linux, it's dot is the current directory. So ./hw means execute hw that is in the current directory. So what it does then, it starts reading this compiled language, compiled code, but it corresponds to what's happening in the code. So the first thing it does would have done is to include these things. So include is a way to include another file, but really what you're going to do is you're going to include what's called the interface to a library. So I need an interface. I need to be able to use IOStream. IOStream is a library that deals with I/O, so printing of a string is an example of output of I/O. And I'll need strings, so I'll have to include strings. So these are two libraries that I've just sort of hooked into. And if I don't, C++ doesn't know about them. So this is one of the cases where the language itself doesn't provide strings as such. It doesn't provide output as such. You have to load a library or at least sort of link to it. And this is how you do it. These include statements. And then there's a thing called int main. We'll see that this is a way to write a function in C and C++. And in essence, everything that you can execute in C++ is a function. It's one of these subroutines. But as I said, subroutines do not do anything by themselves. They're just functions. They're just something that can be executed. So how do I even get an application started? And so the convention is, or the standard says, that there has to be one very specific function called main that will be called as soon as you start a program. So main is where you enter your execution path. The fact that it has an int in front means that it will return an integer. It will produce an integer number at the end. So that's where it starts. And then the block of code that is part of this function has to be between curly braces. Curly braces are the way in which C and C++ denote code blocks. So I want all of this to belong to int main. And then I create what's called a variable. So the variable is called message. It's a string variable, so we have the type of the variable has to be declared first, the name of it, and then I can assign it a value. In this case, hello world. And then I can print it by using this funny streaming notation into std cout. Cout is console out, so it writes to console, and std is standard. I want the line to end, so I want the cursor to go to the next line in case I want to do anything else. And then once it does that, it prints hello world. Note that every statement has a semicolon to end. If you forget them, which you will because you're typing, and sometimes you forgot to type something, the compiler might give you some odd errors about what's happening in that line, and it turns out you just didn't terminate it. So that's what the semicolons are for. And then there's this funny return 0, so that returns the value. That is to say, this function is supposed to produce a value, an integer. Return is a way to produce that value, and here it produces the value 0. Now it produces the value, but where does it go? If this is a function, this is an application, I ran it. Where does this value go? It's just like, well, it's given back to the prompt. So once you've run this, and although you won't do that often in this course, it's good to know, you can actually get this back. If you're in Bash, in the Bash shell, there's a special variable within that shell. So this isn't C++, this is the shell itself, called $?. And if you echo that, that's the value you got back from your int main. This is a useful way to indicate, for instance, that something failed. And by convention, if your program fails, it should return something non-zero. If it's successful, it should return 0. So here, this tells us that this was a successful program. Okay, so it's not lost. The returning of the integer is there for error reporting. Although mostly you won't use this much, it's good to know that it goes somewhere. Notice that I've put these /s here. That's how you put a comment. A comment is ignored by the compiler, but it's useful for you to know what the code is supposed to do. This is a bit over-commented. Obviously, you don't have to spell out everything, but you should properly comment your code to make sure that it's as understandable as possible for others and for yourself in the future. This is summarizes where we were. I think I touched on all of those. Yes. So that's what a C++ program, the simplest one, more or less looks like. And it already shows libraries, it already shows outputs, it shows functions, it shows variables. I'm not hiding anything here. This is clear. Questions? I know if you've done C or C++ before, this is like, why this seems like a waste of time, maybe it is. But I want everybody to have a sort of common ground here. Okay, so let's talk a little bit more about variables. So variables are really named pieces of data. Somewhere in the computer's memory, I have the string hello world, and I just basically gave it the name message. And I can refer to this string now by this name. Now in C++, different from, say, Python, variables have a particular type. This thing called message can only be a string. It can become an integer later. I can't have another variable called message that is now an integer, well, not without giving up access to the previous one. You can store data in there. You can manipulate it, so you can change it. You can assign it. You can add to it. You could, I guess, append to the string. But you can't reuse the same name. So C and C++, Fortran 2 are strongly typed languages. Each variable has to have a certain type. This may seem a bit pedantic, but especially in a compiled language, it's a good thing. if certain things don't match, for instance, I try to add two variables, one is a string and the other is an integer, it doesn't make much sense, right? At compilation stage, it will tell me that, not at runtime. So in Python, I could write a string plus an integer, and I would be no problem until I hit that particular line in the code. In C++, if I try to do that, as I'm compiling the code, even before I'm running it, it would give me an error saying you can't add these two things. So knowing what the types are is a useful strictness to your code. Then the syntax of variable declarations in general is just first to say what type the variable is. Since they have to be strongly typed, you give it a type and then the name. And then you can or cannot. So whenever in syntax I do these square brackets, it's an optional thing. You can assign it a value right away. So you can say, okay, we did that with a message, a string message equals hello world. But I can leave out the hello world as well. And then I just have this memory block. There's different types I can have, even by default. You can extend this, but this is sort of the default set. You can have floating points, so fractional numbers, complex numbers as well. You can have integers of different sizes, integers that are only up to about 32,000 are shorts. Then we have integers, longs, long ints, long ints. You can have characters or strings of characters, so we used std string. You can have a Boolean, which is a yes or no, true or false type. And then you can have arrays or pointers, classes, structures. We'll come back to these in our data structure class in more detail. I have a few slides on them here just as a preview, but we'll look at them in more detail later. Something to note, and especially if you're new to compiled language, is that if you don't assign a value, it is not initialized at all. It isn't set to 0. It's just set to whatever random number is. So as soon as you execute this code and this variable has to come into existence, the computer gives you a location in memory where this variable will sit. And whatever was in that memory before stays there. So this could be 0, but it could also be some random garbage from the previous application you were running or from the previous function you called. So it's a good idea to try and initialize all your variables pretty much as soon as you declare them, or at least right after. My rule of thumb is if you declare a variable, then in the same window as I'm editing, I should be able to see where it is set. If I have to scroll down 2 pages to see where it was set, that's not right. Here's some, I won't go through these, but these are some examples. Once you've got your variables, you can do things with them. You can reassign them. So here, this isn't bad because I'm assigning A right after. Not a big deal. And again, B is assigned right after. So this is assigned. You can do all the things that you would think you can do. You can add to a variable, just add f2d, that's just plus equals. Strings are there, bools are there. It is not 2016. And I did update my slides from last year, as you can tell. Okay. A function, then, so we have variables. We want to act on the variables. We use functions. It's basically a piece of code that can be reused. And it sort of has 3 parts. It has a name, just as a variable. If I want to use a function, I have to use it by name. It has a set of arguments that it gets. So those are basically the input. And then it returns some variable of a specific type. All the types of the arguments, as well as the return types, have to be specific. And these 3 properties together are enough for me to know how to use a function. Because I have to know what I have to put in, and I have to know what I expect to get out. Because if I want to assign it to a variable, that variable has to have the right type. So I have to know the return type. And I have to know the name. So this is called the signature of the function. So it's what kind of arguments go in, what goes out. And so if you want to call the function, that's enough. I only need to know how to use it. I don't need to know what it does, how it's implemented, just to call it. Somewhere it has to be implemented, right? I have to tell the computer somewhere what this function does, but I don't have to know that to use it somewhere else. It just goes and finds it. So all you need to use a function is to declare what it expects as input, as output, and what its name is. The actual definition will be in some sort of library or a different file, and that's fine. So this distinction between a declaration, which is just saying this is how it's used, this is sort of the user manual, and the actual nuts and bolts, that's the definition, is a useful definition to keep in mind, a distinction to keep in mind. So only those declarations are needed, and they are put in so-called header files that are in the include statements. So whenever I have those include statements, it's not reading the actual definition. It's not reading what it's really doing. It's reading how to use it. That's all it needs. If I want to make a function, we saw an example in main already. If I just want to declare it and say, okay, this is how, there's a function that's called name, and it expects these arguments and these return times. The arguments are just comma-separated declarations of variables again. So int main is a good example. This is the most generic way you can write int main, where it can accept two arguments. One is an integer that tells you how many arguments there are, and the other are basically string variables of these arguments. They would come from your command line. If you have a command line and you enter things after the name of the executable, they would go into those arguments. And it returns an integer. This doesn't implement it. This just says such an int main exists. If I want to implement it, it's almost the same, except I do not put a semicolon. I do not terminate the declaration, but I let it be followed by a block of code between curly braces. Okay? So whenever I call the function, now this block of code has to be called. When I want to call it, there's a couple of ways you can do it, but the most easy to understand is to take that name again, give it a couple of arguments, so now just the names of variables that you want to pass, and assign it to a variable that is of the right type for the function. So if I wanted to assign something from the output from main, the var better be a variable of type int. If it is possible to just ignore the fact that it gives output, so you could just say f name argument list, just name argument list. Or you could pass one function to the next function. So here, I could pass the output of name to yet another function that might be called f. So if your code is very sort of functional, you would see that a lot. Example is always better. So here's an example of including first the header file of math functions. They're called cmath because they come from C. This only includes these prototypes, not the actual code, and that's all we need. Now let's say we want to declare that there will be a function called arithmetic mean that takes two variables, a and b. They're both double precision numbers, and then returns another double. This hasn't specified how it's done, but just that such a function exists. If I want to specify how it's, so I can now use this, because I've said how I can use it in an int main. So here's an int main. I define two variables, x and y, give it a variable, give them a value, define some variable z, and then assign to z the result of the arithmetic means x, y, and return the value. Now, this will compile. I can give this to the compiler, but it will not compile completely because I'm missing what actually has to be done with arithmetic means. So once we come to modular programming and how to split things up, we will see that we can put the actual body of arithmetic mean in a different file and compile it separately and then link them together after. This is a simple example, so to make sure that it compiles fully, I have to tell the compiler what to actually do when it wants to call this function. So I have to give the function definition or implementation, and here it is. So it's the same form, no semicolon, curly braces, and it just returns the square root of a times b. Square root is the function that came from math, if you wondered why I had to include math. Square root is only there if I include cmath. All right? So this would compile if I give this to G++, and then the name of the file, it would create an executable, and it would return the square roots of the square of those two. Convert it to an integer because it has to return an integer. So this is a bit of a funny example where I didn't want to bother with printing it out, but let's see. I think this is a good spot to stop. Any questions so far? So we'll continue next week, Tuesday at 11, same spots, same guy. And any questions in between, or if you have trouble setting up accounts, or either email us or come talk to us right after, and we'll make sure everybody is on board. All right?